Okay, so thanks a lot for inviting me here to present a general overview on JCMsuite. So the title is Optical Simulations with JCMsuite. So I do not really go into any details, but rather show the general overview on our software, our company, and then also various applications in optics, including also photovoltaics, but only as one of the examples. Yeah, and I'm from JCM but I also have an affiliation with JCMsuite Berlin. So this is why this is put here also. Um, okay, so the background of JCM is it's a spin-off company from JCMsuite Berlin, still based also in the same building. So we are renting rooms here in ZIP. And we develop a simulation software based on finite elements and also expertise for photonic and nano-optical applications. So our product is mainly the complete workflow as offered in JCMsuite, but of course also expertise in consulting projects and so on. And we have a user base and cooperation partners in the industry. So this is, for example, semiconductor industry, optoelectronics, optical metrology, and stuff like that. Then also institutes of standards, so the German Physikalisch-Technische Bundesanstalt, for example, or US NIST. And then, of course, we have a broad base also of academic users and cooperation partners, like KIT, for example, which we are very happy about. And Carsten already had this image here of James Clerk Maxwell. So JCM is the initials of James Clerk Maxwell because the focus of our software is typically on optical applications where Maxwell equations have to be solved. Okay, so this here. Sorry. Okay. So JCMsuite is a simulation software package for the design and analysis of complex nano-optical systems. So it contains various modules. First of all, a meshing tool. So we have a cut tool to describe complex geometries, and then also a mesher to make tetrahedral meshes, or also prism meshes or mixed meshes, also 2D meshes, 1D meshes, and so on. And then on these meshes, we use our finite element method solver, which supports also HP-FEM. So I'll come later to that, what that is. So this is an typically very efficient, accurate solver. So say our main niche where we operate is typically where people need efficient and accurate solutions for specific problems. So typically this is why we are typically in the nano-optical regime, where we have small computational domains, where this efficiency and accuracy is still reachable with rigorous methods. Okay, then we have general material models, stuff like birefringence, anisotropic material for modeling chirality, and so on. We have dedicated post-processing, like efficient far-field transformations on isolated computational domains, or quite sophisticated imaging solver where aberrations and optical systems can be modeled. Then the solutions can be visualized with our tools. We have also interfaces to MATLAB and Python and can use that for automatic script generation, so for efficient optimization or analysis. There are also interfaces to C, so you can also implement the solver into other frameworks so that it's ideally suited also for digital twins, like here in this SolarTAP project. Then there's also computing cluster support, so you can run computations on different nodes of a cluster easily and distribute the simulations to the different nodes. However, you can also distribute a single but very large computation on different nodes of a cluster. And then finally, there's also an analysis and optimization toolkit based on machine learning. So this is essentially what Carsten also presented in the previous talk, a framework based on Gaussian processes and Bayesian optimization, but nowadays also includes some machine learning tools or some, say, yeah, more deep learning tools. Okay, and then typical applications include lithography, waveguides and fibers, light sources like LEDs or nanolasers, and then also non-structured materials and metasurfaces. So this is somehow the field where solar cells where with nanostructures are located. So this is how we typically enter the field of photovoltaics. Okay, in JCMsuite, we don't have only Maxwell's equations, here electrodynamics, but you can couple also a continuum mechanics solver to that. For example, when you have bending or when you have thermal expansion due to heat transport. And we have also heat transport solvers, so you can, for example, model that the light field you have in your device heats up your sample or your device, and this then leads to thermal expansion, which can lead to bending or to stress. And then via photoelasticity, this changes the optical properties again, so you can easily build loops here for self-consistent simulation of multi-physical devices. However, typically we concentrate on Maxwell's equations. So there we work in the frequency domain. So it's usually solved with a time harmonic Maxwell's equations where we concentrate on one specific wavelength. And then for a wavelength scan, we have to do various simulations at the different frequencies. However, Maxwell's equations can be divided into three main problem classes here. This is scattering problems, where you have an external light source illuminating your sample, like the sun impinging on a solar cell. And then you want to solve for the scattered light field and for quantities deduced from that. However, sometimes also it's more useful to look into resonance problems or to additionally look into resonance problems, like in the case when you have a cavity, like for a laser, and when you want to know the resonance wavelength, the Q factor, and stuff like that. Or sometimes you have waveguide problems where light is propagating through a waveguide which is invariant in one direction and might have nanostructures included, like in this photonic crystal waveguide fiber, which is indicated here, and where you are interested in the propagation constant, the modal field, and derived quantities from that again. Okay, so we use these problems using finite elements. So why are we doing that? There are various advantages in FEM. First of all, probably it's its geometric flexibility. So in real-world devices, you can have very complex structures like these helices here, for example, which would be complicated to solve with staircase discretization, especially when metals or high index contrasts are involved. At each staircase, you would have artificial fields, which overall typically spoil the accuracy of the results. And then in these examples here, you see, for example, that effects like angles in your geometry, sharp corners, or rounding typically do not lead to additional computational costs in your meshing. It's just that some nodes of the unstructured mesh are shifted a little bit. So therefore, this can be very efficient. Then we can handle multi-scale structures. So often you have some very thin layers, few nanometers only. Also in solar cells, for example, often there are very thin interlayers, whereas other layers might be microns or more thick. And in the meshing, the mesh can adapt very nicely to such thin structures and still preserve the accuracy of the geometrical representation. So this is what our mesh generator does, creating such a mesh. And then when we have created a mesh. We compute the solution to Maxwell's equations on that using so-called finite elements or mesh elements, vector elements on these meshes. And there are typically two different parameters for reaching higher accuracy here. So the size of a mesh element, like this triangle in 2 dimensions, the larger the size is, the poorer is the approximation quality. On the other hand, we have also the polynomial order of the finite elements, which are used to approximate the solution on this single mesh element here. And when the polynomial order is higher, the approximation quality is increasing. So therefore, typically, one does not really know what to do, decrease mesh size or increase polynomial order in order to reach the best accuracy. However, what can be shown theoretically is that the best convergence property can be reached when you have a full control of both of these. So you can vary the mesh elements and then use in different regions of your solution field also different finite element polynomial orders. Like in these examples, you might have also due to geometric constraints very small elements here where you can use low order elements p equals to 1, and then other regions where the field essentially behaves more like a normal wave. It's typically advantageous to use higher order finite elements. And all this can be steered also automatically using adaptive error control and error estimation. Okay, then also singularities, which often play a big role, can be resolved by using adaptive error control. So when you have, for example, metal sheets with sharp corners, you might have these very steep singularities at the corners, and mesh generation and adaptive meshing using error estimation can then create very fine meshes at the singularities, and it can be shown that then you can get very accurate numerical results also in these cases. Okay, then as Carsten also introduced in his slides, we also have optimization tool for parameter reconstruction, sensitivity and uncertainty analysis, and also for optimization. So therefore, we have a toolbox. So it's based on Bayesian optimization regression. It optionally includes also forward differentiation. And yeah, we can create a set of cheap surrogate models based on Gaussian processes, which are then used to determine, for example, next sampling points in an iterative training where an expensive model has to be solved. So typically we start in a high dimensional parameter space with a few observations, then we build up Gaussian processes on that. So this is a continuous model on the full parameter space, and this gives us an estimation of where the model is accurate and where it's not accurate already. And also it gives an estimation where objective functions can be reached or can be improved. And this allows then to construct an iterative method in order to build up a relatively small basis which still captures the full physics on the whole parameter regime. Then also this last point here is Bayesian target vector optimization. So often we have measurements or we have optimization targets where not a single scalar is the optimization target or the measurement, but in the measurement you might have, for example, various diffraction orders. And we can build up Gaussian processes for all of these diffraction orders then in order to reach a much faster convergence in the inverse problem. As Carsten has mentioned also in his talk, often it's very useful to have parameter derivatives. So when we compute our light field in some device, we typically derive some quantities like the intensity. And then in the device, we might have some free parameters like this width and height of this line here, for example. So we compute the intensity here as a function of these parameters, and also the full light field here as a function of these parameters. Now we can also, by constructing a mesh which knows how it will change when these parameters are varied, we can also compute the derivatives of these intensities here, or of the full light fields, or of other derived quantities. And this can be done for, in principle, many free parameters here, and also it comes at nearly no additional computational cost because we can reuse our previous forward or previous, say, inverted system for the forward solution. And therefore, yeah, we get these parameter derivatives nearly for free. So this can be useful then in inverse problems. Okay. And as I said, we have HPC and cluster computation support, and here are some results for distributing a single computation on a cluster of computers. So the example here is a metamaterial lens, a meta lens, where we have a relatively large arrangement of arbitrary scatterers. So the field of view here is something like 50 microns or so, I think. Typically, it's very costly to get an accurate solution on a large computational domain, or it gets even impossible. However, what you need is a large memory, and typically a single computer gets at the limit of its memory at some stage. So therefore, we need this solver for distributing this on a cluster. And of course, often in the literature, you see results where you can use also approximative methods for constructing such resulting light fields here, for example, for computing them. However, as I said in the beginning, our niche is really high accuracy results, which are in some niches, it's necessary to have highly accurate results. And for that, this is essential. And for that, most of the methods you have otherwise are not feasible anymore because of convergence problems. Okay, and these are some, so this is relatively new. So these are also some relatively new results. So here you see for the computation before how the computation time is scaling with a number of unknowns. So the number of unknowns for this FEM simulation is here between something like 2 million and about 100 million or so. And you see that here we have some linear, or we have some scaling which goes like the number of unknowns to the 3/2 roughly. But then at something like 10 to the 7 unknowns, it gets even better. And this is due to the setting here that at a certain memory limit of something like probably 128 gigabyte, I guess it was here, the computation is distributed to several nodes. So you see that you can solve problems here, then also on your cluster, which on the single node, if it would be limited by this limit here, would not be feasible or doable anymore. And then here you see the total memory usage going up here, and yeah, it's always limited. Okay, no, it's something like 500 gigabyte or so, or 600 gigabyte, I guess, was the limit here. So from here on, it's distributed onto several nodes. Okay, so these are possibilities for computing large-scale problems also with finite elements. What we've implemented also is to use out-of-core computations where some of the computation is distributed to SSD disks. So this can also reduce the RAM footprint on smaller machines like sometimes even laptops or smaller workstations. Okay, and with that, I come already to application examples, and I just have some examples and will go very briefly through them, just to show you that it's a general purpose solver which can be applied in various fields. So, for example, in plasmonics, so this here is from a benchmark computations with many other methods also, where we get relatively accurate results for a high Q resonance in a plasmonic system. So this was a collaboration here with many teams headed by Philippe Lalanne here. Then, for example, quasi-bound states in the continuum, where you have isolated um, resonators, which may be fully dielectric and relatively small, but still you want to reach high Q factors. So this can be reached by a modal interference of various of the modes which are supported by by this geometry. So the geometry can support energy or at the same energy various modes where the radiated field then interferes with the field of the other modes, and this essentially leads to so-called quasi-bound states in the continuum. And here you can see also that we can use modal expansion methods to explain the physics which is going on. So we have also so-called quasi-normal mode expansion methods, which rely on dedicated methods for that, which are also rigorous in the sense that they also take into account a background field. Then we work a lot on future quantum dot-based single photon sources for quantum computing and quantum communication, for example, together with Stefan Reitzenstein at TU Berlin. So they have specific experimental equipment in order to generate relatively complicated setups where quantum dots are embedded into cavities, for example, with DBR layers here as a back reflector, and then with lenses in order to increase the outcoupling from of the quantum dot here into specific directions. And yeah, it's in principle a co-integration of micro-optical arrangements and quantum dots. And we analyze here Purcell enhancements, specific modal structures of the device in order to get a directionality of the light field and so on. And also here we have optimization problems typically because all of these layers, of course, can be controlled with a nanometer precision. Okay. So another example for that is circular grating resonators, where you have these circular gratings, and here we also show a modal expansion of the far field patterns. So even though it's in the far field, we can use our computations to get an accurate representation of say the origins of the light field in the far field in the different modes in the structure, which then again can be used to optimize the structure. So typically you want to reach such a setting as here on the right-hand side, where a single mode is responsible for the radiation into only a very small opening. Okay, then this is an example from computational lithography. So in lithography, you want to optimize nanopatterns on your photomask in order to reach specific stable images in your resist on your silicon wafer in order to be able to print reliably very small structures in lithography. So here the cooperation partners Nikon Corporation. We also cooperate in this field with ASML. Okay. Then related to microfabrication is always nanometrology. So in the semiconductor industry, typically you want to control various processes in order to stay in with your critical dimensions into the fabrication windows, such that the computer chips which are produced are produced stably, and therefore during the process typically you have measurement steps. Um, and this is used for overlay critical dimension metrology. However, also for improving performance of coordinate measurement machines, which are similar to microscopes often. And this process control is done in various wavelength regimes like near-infrared, visible, EUV, but also at X-ray wavelengths. Here we have mainly cooperations with metrology institutes, and we have a user base also in the industry. So a typical setup looks like this. You have some radiation source, and then you have various reflected beams which are detected with some detector. So this needs to be modeled, and then it can look like this also in the DOV. This is a setup at PTB. The other was a setup at Bessie in Berlin. And you're interested in quantities like the width here, the height, the corner rounding, and so on, and want to measure that optically and not in electron microscopy because this destroys the sample and is too slow. And then this is how a typical result from PTB looks like. So for various illumination settings and various observation angles, down here you have intensity values. And here again, you see optimization results. So when doing optimization, we try to fit the three parameters in our models in order to reach a good agreement with these experimental results. Because we do this by using Bayesian optimization, we get the surrogate model, which then can be used also to perform a sensitivity analysis. So for that, we can do a Monte Carlo sampling then of the surrogate model, which involves a lot of samples, but because it's a surrogate model, it's very fast, so this can be done reliably also. Here in this left image, you see also that we often compare various methods with each other. So here we have this Bayesian optimization method, which gives a very good results result even after a very short time. So few forward simulations only. And the special trick is here that we use this least square Bayesian optimization or target vector Bayesian optimization. This is the second citation here, which takes into account all the information from the measurement. So all these different values of the experiment are used, and surrogate models are built up for all of the measurement values and not only for one of them. Still, you see this is computation time here, so it can be done efficiently and does not take much more time than the others. But it leads to very good conversions, at least in this case here. Okay, then we have metamaterials or nanoplasmonics, where we have a lot of collaborations. This was a very early result here, in collaboration with a group of Martin Wegener and Sukulis. On split ring resonators, where we have a nice agreement of experiment and theory. Then these metamaterials nowadays get more complicated, so this is already 10 years old. Also, these are metal helices made by laser imprinting, essentially. And this is a recent result with helices built in self-assembly. This is a collaboration with Tim Liedl at LMU, where nanospheres are attached to a DNA origami in a deterministic way. And you see here you can build deterministically structures with 1, 2, 3, and so on. Nanospheres which wind up like a helix along this DNA origami here. And the nice thing is here, you do that in a solution and you do millions or billions of these helices in the same time. So it's a very fast fabrication method. Okay, and then you see nicely in experiment and theory that you need at least 4 of these nanoparticles in order to get a decent circular dichroism signal. This means that left-handed and right-handed circular polarization is treated differently by these helices, which have also a winding. However, what was interesting here also is that in the experiment you also see a signal for only 3 particles, which is quite significant. So this was not understood in the beginning. However, in the simulation, when taking into account a coupling to the DNA structure, which has a different dielectric index than the aqueous surrounding, then you can again reproduce these experimental measurements here also in the simulation. Okay, then often we look at resonance effects. Typically, resonances enhance performance, and this is typically a main driver for nanophotonics, that you can use this performance enhancement for various experiments and in the end devices. Here you see photonic crystals, large-scale photonic crystals made at Helmholtz Zentrum Berlin. And you see that experimental simulation of the angular resolved, so the angle is here to the right, reflection spectrum agrees very nicely. And in the simulation, you can also see that for specific wavelengths, you also reach a very large field enhancement. This can then be used, for example, to excite quantum dots, which are located close to this photonic crystal. And here you see that the quantum dot photoluminescence signal can be greatly enhanced by techniques like that. So this is in principle then also interesting for future photovoltaic devices where you might use some photoluminescence or recycling of photons which are absorbed in one layer and could be transferred into another layer of a multi-junction cell, for example. Okay, and then finally here, this is a result from Helmholtz Center Berlin again, where they have designed and then also experimentally fabricated a silicon perovskite tandem cell, which was one of the dots in the plot which Carsten also showed earlier today, because it was a world record efficiency at that time with about 30% PCE. And the structure in that case is periodically sinusoidally modulated, which can be fabricated by impressing techniques. And of course, it's then also a nice problem for finite element modeling, because you have a periodic unit cell which is not too large, so you can get accurate results. You can nicely steer these geometries and parameterize them and then do optimization and so on. Okay, and this brings me to the end. So I've shown you our simulation software JCMsuite and shown you some application examples. And yeah, with this, many thanks for your interest.